I can feel the confusion about entropy. There are incomplete explanation and lack of understanding. In this video we will try to make it more clear, and we begin with the strongly misleading. Some say the increasing entropy is cause of increasing disorder, but there are many cases where high entropy means more uniform distribution. Thus order have no exact match with entropy, and it's better to discard this way in explaining the concept. Entropy is usually related to temperature. We know an ice cube melts and the coffee cools down. These are systems with significant difference compared to the environment, so they are considered with low entropy, and interactions brings toward a state that flatten this delta. This process depends on the system's ability to interact. In fact, with a thermos insulating this content from the surrounding, it doesn't matter if the content is hotter or colder, the exchanging process becomes slower and it will take much longer to achieve the same result. In the ideal case, we have a closed system where no exchange takes place. Whatever is inside is isolated and unaffected by the outside. We consider this container a macro system, and we place inside the two objects with different temperatures. The previous process will also take place here, with the macro system having low entropy in the initial condition, and over time the entropy increases. If we now add another piece with different temperature, both lower or higher, it won't matter, we are creating a new initial condition with again low and increasing entropy. We are looking at how energy moves, and this displacement is what we exploit to do work. We can consider this entropy as the process by which energy is diluted until it can be used for any further work, and what is left is just heat. Since energy is conserved, initial and final quantity are equivalent. What is changing is the quality of such energy. Temperature is the kinetic energy of atoms. So here we are considering interactions related to Newtonian mechanics. Looking at two systems with different kinetic, forces are symmetric but interactions are inelastic, and the more excited wheel sees more energy. The second law of thermodynamics states that entropy of a closed system cannot diminish. It tends to increase, or at least it remains stable on average. Even if you could achieve perpetual motion, that machine would at best sustain itself, and it wouldn't generate additional power to supply external devices. Strictly following the second law, not even perpetual motion is achievable because you can't reach 100% efficiency. And even if you somehow work around the second law, you can't break conservation of energy, so it would still be pointless. With Boltzmann, entropy becomes statistical. The system is not in thermodynamic equilibrium until energy is evenly spread. So the initial condition is considered with low entropy, and the systems evolve toward higher entropy because this configuration is the more probable. Using microstates, we can extend the action of entropy beyond temperature. A typical example is the arrangement of gas particles in a closed environment. The two systems with low entropy have different macroscopic properties compared to those with high entropy. So initial and final conditions are different macrostates. Microstates, on the other hand, refers to the main internal arrangement that the macrosystem can have. The one with higher entropy has energy more spread, and so a larger number of equivalent microstates. It can be many different configurations without changing the macroscopic properties. On the contrary, the macrosystem with low entropy has a lower number of equivalent microstates. Since these are closed environments, the quantity of energy and the number of particles doesn't change over time. So the amount of possible microstates with both low and high entropy is the same. It is the quality that is making the macroscopic difference. Entropic evolution isn't just the overall count of microstates. It's about how many states are possible without changing the macroscopic properties of the system. With more uniform distribution of energy, there are way more equivalent configurations and we state the entropy is higher. Here it's usually implied an initial unstable macrostate that will inevitably evolve toward higher entropy. From a statistical perspective, we still account for the very unbalanced microstates. But with uniform distribution of energy, there are way more equivalent configurations. Despite each independent arrangement has the same probability, most of the total microstates are the indistinguishable of higher entropy. Thus, over time, this configuration always becomes the more likely. It means that the microstate will be found more often with uniform distribution of energy, up to the point where, with large numbers, the strongly unbalanced microstates becomes almost impossible to find in the high entropy state. The increase of entropy implies a change of the macrostate with respect to the initial condition, and it's said that the system undergoes statistical evolution toward more microstates. However, probabilism doesn't explain why energy behaves this way. Statistics of microstate is not the mechanics that fuel physical processes. Like, a surface can be statistically flat, but it's not flattened by statistics. And entropy is more than a temperature-driven behavior. We see that with liquids. Both when they mix and separate, we are watching the entropic progress of the system. We can say the initial state is unbalanced even if the two evolve in opposite directions, and it's not because of temperature. The same goes with the particle in a box, because now the systems are electrically charged, and the entropic behavior will depend much more on Coulomb than thermodynamics. So, balance and uniform distribution are selective statements based on knowing what will happen, and they can refer to opposite evolutions. It should be noted that all these behaviors are spontaneous. Whether I place a ball on a flat surface and stays put, or when it rolls down the slope, we are dealing with spontaneous behavior because everything in the universe is spontaneous, so it's an unnecessary clarification. The only behaviors we can observe that are not directly spontaneous are the actions of life forms. Irreversible processes are also associated with entropy, those who can just evolve in one specific direction. Here too we have the same selection problem as with order-disorder. This is part of a complex construction cycle, and it does indeed show a univocal direction. But entropy also includes interactions without these specifics. So again, there is no exact correlation between entropy and irreversibility. And are we sure that the number of eggs in the universe must decrease, or that ice can only melt? The entropic trend of the second law applies to closed systems, but the boundaries of these systems are fundamental in defining the trend. If I enlarge the confinement, I decrease the entropy without changing the content. In the real world, it's virtually impossible to have a perfect closed system, and the bigger the enclosing, the meaningless the boundaries becomes in affecting the internal entropy. Interactions are local, and their range doesn't scale with size. Most of the confusion with entropy comes from definitions that are not always suitable. Sometimes they even contradict each other, and specific context must be selected to make the concepts hold. In thermodynamics, interactions are simple, and macroscopic results are easy to track and observe. Kinetic energy tends to uniform, so entropy is widely explained with energy wanting to spread. Therefore, it's hypothesized heat death as the last phase of the universe, with even temperature and no more work available. But heat death could happen if thermodynamics were the only fundamental force driving the evolution of the universe. Physics is way more than temperature and Newtonian mechanics, and on large scale, gravity makes the contradiction clear. Gravity is a huge energy aggregator acting against the second law of thermodynamics, also with 100% efficiency because it's conservative. Even more, it's capable of very long-range interactions, way beyond the locality of temperature exchanges. More in general, all matter is energy stable over time that doesn't spread. And if I put the crystal in a closed desert, thermodynamics evens out the temperature, but it's also concentrating more energy in the system. Moreover, for as much kinetic thermodynamics can spread and move, matter carries amount of energy that are orders of magnitude greater. A piece of steel at 1000 degrees seems to carry much more energy than the same at room temperature. I wouldn't touch it, but additional energy by kinetics compared to the quantity contained in matter, it's so little to be in practice irrelevant, and the two weight the same. As example, this is the energy released by a few hundred kilos of matter, and it's not even annihilation, it's just some binding energy. So when we look at how temperature behaves, we are considering just a tiny fraction of all the energy locally present. We need a wider perspective than just mechanical interactions. Defining thermodynamics as the only engine for entropy, most of the events are ignored. In the universe, many interactions occur simultaneously, and in structured systems, the number of additional emerging factors is disproportionate. As example, on Earth we mostly have ice melting into liquid by thermodynamics. This state is stable thanks to the atmospheric pressure, and we need energy to make it gas. On the other hand, in space, liquid water is highly unstable and the entropy evolves toward vapor because of the vacuum. Almost always this gas becomes ice crystals, but the process is not because of temperature, it's electromagnetism. The combination of all these factors defines the evolution we observe and we call entropy. Some may converge to the same result, but many are conflicting. Within interactions, energy aims for stability, but every force has its own direction, to the point that stable hardly means constant, and at best it's small fluctuations. So even if the straightforward entropy of thermodynamics actually tends to the evenly distributed energy, many other entropies can act in the opposite direction, creating a much more complex reality, hard to define with simple and strict rules. And it must be stressed that all these events depend on particles interactions. Fields and waves don't have proper entropy and they need special evaluations. Since stability doesn't have a straightforward meaning and the evolution is context dependent, entropy can be thought as the emerging macroscopic result combining the effect of many interactions. On one side we have conservation of energy as quantity, on the other there is the qualitative evolution of entropy. While the former is consistency with continuity, the other is the dynamism, because we can destroy, but we can transform energy. Thanks to the property of matter, second law can be violated without violate conservation of energy, because thermodynamics are just the easiest piece to see of a much bigger puzzle. Thereby, it's hard to believe in heat death as the final solution, unless you can somehow inhibit all condensing interactions. Moreover, even accepting the universe as a closed system, when we combine a large amount of matter, huge distances, and locality of energy, we see a behavior very similar to that of an open system. Sectors at different stages have different entropies that can feed each other. Before radiating energy, a star must ignite, and even explosions are matter that is spread out but that can cluster again in other systems, since at the larger scale, gravity is the one ruling. Given the general appeal for conservations shown by physics, one might also speculate that, overall, even the quality of entropy is conserved.